Hey guys, this is Aaron Carmen from AXE Electronic, back with the next video in our circuit analysis lecture series. So today we're on lecture number 22, and we're going to be looking at some examples for AC power. So in the previous video, we talked about AC power and kind of got an intuitive feel for it, and then looked at the different formulas for AC power that we're going to need. We also introduced the concept of the power triangle, which I think is the best way to relate all these different quantities using a graphical method and something that you might be more familiar with. So today we've got 3 conceptual examples and then 3 circuit examples. Now the reason I only did 3 and 3, because if you remember whenever we did AC circuit analysis, I actually did 5 and 5. The reason I only did 3 and 3 is because we really haven't talked about as much stuff, and AC power, as far as plugging this in and doing the different stuff, I think it can be a little bit easier. So you don't need as many examples. You just need to do a couple examples to get a feel for it. Okay, so we're going to start off with these 3 conceptual ones and then look at actual circuits and look at the AC power in them. Okay, so let's go ahead and get started with our first conceptual problem. So up here, we've got determine the real power, reactive power, and power factor of the following apparent power. Now remember, apparent power is the formula S is equal to 1/2 VI conjugate. Okay? Now, if you don't know why we have that 1/2, or if you don't know why we have that conjugate, go back, watch my previous video because I explain it in more detail there. Okay? So this is a complex value. Okay, so it's going to have a magnitude and a phase. The magnitude is 40. The direction is 30 degrees. Okay? So what I think is most helpful to get the real power and reactive power is going to be to draw this on the complex plane. Okay, because this is a complex number, we can draw this on the complex plane. So let me go ahead and draw a plane for you. So here we're going to have the real axis and the imaginary axis. And I'm not going to be too precise on this, so I'm just going to draw this vector here for apparent power. So I'll call this one S. I'll make that a little bit neater. I'll call this one S. Now this S has a magnitude of 40, so the length of that vector is 40, has an angle here of 30 degrees. Okay? So this is how we're going to represent apparent power in the complex plane. Now, what we can do to get real power and reactive power is we can break this apparent power down into its different components, okay? Because you'll see it has a real component and an imaginary component. Now this real component is going to lie on the real axis. So I'm going to show that in blue here. The real component, you guessed it, is going to be real power, P. Now it also has an imaginary component, and that imaginary component goes straight up because it's purely imaginary. That's going to be Q. That's our reactive power. So you can see this is forming a triangle with P and Q as the sides and the apparent power S as the hypotenuse. So now instead of having to just memorize those complex formulas that we had, if we can just draw this power triangle, we can use those trig identities that you practiced in high school and that you've gotten really acquainted with and you should be pretty familiar with. So what we can do to find the real power, I'll use blue here. The real power is just going to be the magnitude of this apparent power, so I'll do the magnitude of S, times cosine of the angle 30. Okay, so this is going to be 40 cosine 30. And if I plug that into my calculator, I'll get 40 times cosine 30. That's going to give me, that's going to give me 34.6 watts. Okay, the units for real power is watts. If we're talking about reactive power or apparent power, then it's not watts. If you don't remember those, I'll remind you of them as we go. But if you need to get a good explanation of it, again, go watch that previous video where I talk about it in more detail, what these units are. Okay? So now let's do the same thing for reactive power. So reactive power is Q. It's going to be that same magnitude of S, except this time it's going to be times sine of 30 degrees. Now, again, if we plug this in, this is going to be 40 times sine 30, and that's just going to give us 20. But what's the unit of this? You might be asked, what is the unit associated with reactive power? Well, it's not watts, because watts, remember, is real power. So what is reactive power? Well, we're multiplying voltage times current, so volts times amps, and then we need to make sure we note that it's reactive, so the unit is VAR, volt amp reactive. So pretty much that's the unit of reactive power, volt amp reactive. Okay. Now, what if I asked you, what's the unit of this apparent power? Well, it's not watts because it has a real and a real and a reactive. Okay, and it's not VAR because again it has a real part, so we just call the units for S, I'll mark this up here, VA, volt amps. Okay, volts times amps, that's all it is. Okay, so now we've got the real power, we've got the reactive power. You'll notice I didn't put any J's or anything like that here because we only really care about the magnitude of the reactive power, and we know that, reactive power is purely imaginary and real power is purely real. Okay, so I didn't include any of the J's here. If you wanted to, you could use the formula that we talked about previously, that S is equal to P plus JQ, and you can manipulate this and find that this will give you 40 with an angle of 30. Okay? But for now, I'm not going to do that because it only asks for the real power and reactive power. Now, the last thing we needed was power factor. Okay? So how do we calculate power factor? Well, power factor, remember, that's going to tell us how much of this power is real power. Okay, so all this is, if you remember, it's just cosine of that angle, 30 degrees. Okay, so if we plug this in, if I do cosine of 30, then I'm going to get 0.866. Okay, and that's our power factor. It doesn't have any units at all. Just power factor is 0.866. So, this is not really a good power factor. Typically you want greater than 90, greater than 0.9, greater than 0.95, depending on whatever the application is. So this isn't a great power factor, but it's not the worst it could be because it could be something down all the way to like 0.1. Okay, so it's not great, but it's also not terrible. So this is our power factor here, and it's a pretty simple formula, just cosine of that angle. And that's going to determine how much of our apparent power is real power. Okay. So now we've done this first problem, easy, no problem at all. Let's move on to the second one. Okay, so now we're trying to determine the apparent power and the power factor given the following real and reactive power. Okay, so now in the previous one we were given apparent power and we were asked to find real power and reactive power. In this one we are given the real power and reactive power and we're tasked with finding the apparent power first. Okay, so how can we do that? So the way we can do this is that we can use the formula that I actually just mentioned in the previous problem, that S is equal to P plus JQ. So this is going to be 10 plus J2. What's the unit for this? It's VA. It's not VAR, it's not watts, it's just VA, volt amps. So we may not want this in rectangular form. We might want it to be in its polar form. So you can do that a couple of ways. The simplest way would be to have your calculator in polar form and just plug in 10 plus J2. Okay, and that'll give us, I'll just go ahead and give this to you. That's going to give us 10.2 with an angle of 11.3 degrees. Okay? But if you want to know the actual mathematical expression, just to make sure that we're on the same page and that you know how to do this, maybe if you don't have a calculator, all you got to do is say the magnitude of S is going to be equal to the square root of P squared plus Q squared. So if I plug that into my calculator, just to double check, 10 squared plus 2 squared, square root of that is going to be 10.2. Okay, so this is 10.2. And then the angle, that's just going to be equal to the arctangent of Q over P. And this is all just trigonometric identities. Okay, so this is something that you should be able to work out pretty easy graphically. I'm not going to go into it, but I'm just going to give you these formulas. And if I plug that in, arctangent of 2 divided by 10 is going to give me 11.3 degrees. Okay, so that's how we get to this solution here. So this is our apparent power. What's the power factor? On the previous problem, whenever we were asked to find power factor, it's just cosine of theta. And that's all it is still. Just cosine of the angle of the apparent power. So if we plug that in, cosine of 11.3, that's going to give us a power factor of 0.981. So compared to the previous problem, this one has a much better power factor. We're doing a whole lot better with this one because we said a good power factor typically is going to be greater than 0.9 or greater than 0.95. So this is something that's, again, not perfect, but pretty good. So for most applications, this might be just fine. So now we found the power factor, we found the apparent power, we're done with this problem. Okay, so let's go ahead and move on to the next one. Now, this one is just a very conceptual problem, not really numbers at all. It's asking what is the range of power factor? So what is the power factor bound by, if it's bound by anything? And then what is the optimum value? Okay, so we actually just kind of talked about this. So the range of the power factor, remember, power factor is just cosine of theta. Now, cosine is the cosine function is limited between 1 and -1, okay? But we can't have a negative power factor, okay? And you can see that if you have a negative power factor, that really doesn't make sense because that means you're getting negative power back, okay? And that would mean you'd have to be having a source, okay? So we can't really have a negative power factor. So what we'll find is that you can prove it mathematically that the angle of apparent power is always going to be limited between plus 90 degrees and minus 90 degrees, okay? But I'm not going to do that proof for you, and I'm just going to tell you, like I told you in the previous video, that power factor is limited between 0 and 1. Okay, now what is the optimum value? Well, it's probably either one of these. It's either 0 or 1. Okay? And remember, power factor is the ratio of apparent power, or the ratio of real power to apparent power. Okay? So we want all of our apparent power to be real power. So that means our power factor optimum value is going to be 1. That's the one we want. So I'll use green here because this is good. This 0 is really bad. We don't want it. So we want a power factor of 1. All right, so that's the last of the conceptual problems. So now we can actually move on to the circuit problems. So let me draw this circuit out here for you. So we're going to be calculating the AC power for each component. Okay, so we're going to start off with a 10 with an angle of 0 degrees source. That's going to an inductor and a resistor. Now this inductor has an impedance of J 2.5 ohms. This resistor has an impedance of 4.33 ohms. And now I'm also going to give you the current. This current is 2 with an angle of minus 30 degrees. Okay, so you can see that I gave you current. I gave you the inductor and impedance. Okay, I didn't give you the inductance because I wanted to make things a little bit simpler for you, but we know how to convert inductance to impedance. So I gave you just the impedance of the inductor. That's a little bit less work you have to do. So now we can start calculating the power in this circuit. Okay? So first thing, let's calculate the voltages, because we're going to need to know the voltages if we're going to calculate power. Okay, so here the voltage, I'll call this VR because it's just the voltage across that resistor. This VR is just going to be equal to the I times the R. So that's going to be equal to, let me make sure I plug this in. So it's going to be 2 with an angle of 30. Oops, angle of minus 30, sorry. Times 4.33. That's going to give us 8.66 with an angle of minus 30 degrees. And we know the voltage here is just Vs, right? Because we have that 10 with an angle of 0. Now, we know the current through this inductor, right? We know that current is 2 with an angle of minus 30 degrees. We know the voltage, okay? So we can calculate the power for this inductor. And then we also know, let me make sure I'm doing this correctly. Okay, yeah, so then we also know the current and the voltage across that resistor, so we can calculate the power in the resistor. Okay, so let's start calculating powers. So let me use blue for the resistor. If I'm calculating the apparent power of this resistor, that's just going to be 1/2 VR times I conjugate. Now, let me move this down here. That's going to be 1/2 VR, we said, is 8.66 with an angle of minus 30 degrees. Okay. And then our I conjugate, well, our I is 2 with an angle of minus 30 degrees. Now, if we make that a conjugate, that's going to be a plus 30 degrees. Okay. So now let's just plug this into our calculator. So I'm going to do 1/2 times 8.66 with an angle of minus 30 times 2 with an angle of plus 30. And that's going to give us 8.66. Okay? And this is VA, right? Because we calculated in apparent power. Okay? But you'll see that apparent power is purely real, right? So we could also say the real power, we could also say the real power across this resistor is just equal to 8.66 watts. We could also say the reactive power for this resistor is equal to 0 VAR. Right? And all of these things here are true. But typically we're going to stick with apparent power. If you were asked to calculate real power and reactive power, that's how you could do it here. But for now, we're going to stick with just apparent power. So now we know the apparent power for that resistor. Now, how can we calculate the apparent power for this inductor? Well, we can calculate the voltage across this inductor pretty easily. Okay, so the voltage across the inductor, I'll move over here and use green. Voltage across the inductor, VL, is going to be VS minus VR, because that's the potential difference across the inductor. So if I plug this in, 10 with an angle of 0 degrees, minus 8.66 with an angle minus 30 degrees, then what do we get? Well, we're going to get, make sure I get this correctly, we're going to get 5 with an angle of 60 degrees. And I had to round a little bit because my angle was 59.9971, but 5 with an angle of 60 degrees is a pretty nice round number for us to use. So that's the voltage across that inductor. Now, what is the current through that inductor? Well, the current is 2 with an angle of minus 30. So the current is lagging the voltage, which is what we expect for an inductor, right? We expect current to lag the voltage, so we're making sense there. Let's calculate the power for the inductor. So SL, the apparent power for the inductor, SL is equal to 1/2 VL times I conjugate. Now if we plug this in, I'll scroll up here so you can get another look at the circuit. The current is going to be 2 with an angle of minus 30. We calculated the voltage was 5 with an angle of 60. So we can plug this in. This is going to be equal to 1/2 5 angle 60 degrees times the current, which was 2 with an angle of minus 30 degrees. But we're doing the conjugate, so this is going to be plus 30. And what we get is we'll get 1/2 times 5 with an angle of 60 times 2 with an angle of 30. Make sure I entered everything correctly. Okay, and this is going to give us 5 with an angle of 90 degrees. Okay. You could also just write this as, because if it's pointed 90 degrees, that means it's all on the imaginary axis, so you could just call this J5 VA. Okay. Either of these are correct, 5 with an angle of 90 or J5. They're the same thing. So what we can tell is that in the resistor, we had only real power. In this inductor, we have only reactive power. Okay? So for the second to last thing, let's go ahead and calculate the power for this voltage source. Okay? So the power for this voltage source, the apparent power for the source is same formula, 1/2 VS times I conjugate. So what we'll see is that, we're measuring, this is VS, right? We can see the current is going into that negative port, so we know it's going to be negative here. Okay, so we're going to have a negative value of apparent power. So let's plug this in. So we're going to get negative 1/2. The voltage is 10 with an angle of 0 degrees. The current is 2 with an angle of minus 30 degrees. Conjugate makes it plus 30. Okay, so this is going to give us negative 0.5 times 10 with an angle of 0 degrees times 2 with an angle of plus 30 degrees. And this is going to give us, let me make sure, I want to get this in a different form. So I'm going to say this is negative 10 with an angle of 30 degrees. Okay? And the reason I wrote it like this, my calculator actually gave me 10 with an angle of negative 150 degrees. So positive 10 with an angle of 150 degrees. And you can think, that's pointing, let me make sure I'm pointing this correctly. That's pointing like in this direction, okay? So 10 with an angle of 150 is pointing in this direction. If I want to flip it by 180, I can flip it by 180, so add 180 degrees, but then I need to make sure I change the magnitude towards pointing back toward the original direction. So we don't really change anything by writing it -10 to the angle of 30, but it's just going to make more sense later on. Okay? And I'll keep the original notation here just to make sense of it later. Okay? So this is the apparent power that is supplied by the source. So now let's check a couple of things. Let's check and see, how much power is actually being consumed in this circuit. So let's, do the apparent total power. So that's going to be the apparent power for the inductor plus the apparent power for the resistor. So that's going to be J5 VA plus what was consumed by the resistor, 8.66 VA. And what is this going to give us? Well, let me plug this into my calculator. So 8.66 plus J5. That's going to give us 10 with an angle of, not minus 30, 10 with just an angle of 30 degrees. So the total amount of power being consumed is 10 with an angle of 30 degrees. The total amount of power that's supplied is minus 10 with an angle of 30, or 10 with an angle of -150. So you can see that if we add those two things together, they cancel out. So we're supplying the same amount of power that's being consumed, which makes sense, right? Because we always have to make sure that we're obeying the laws of thermodynamics, make sure that we're only supplying energy that's being dissipated. Okay, so this is making sense to us. And just to double check, I can plug in 10, let me make sure, 10 with an angle of 30, and then plus -10 with an angle of 30. That's going to give us 0, just like we expect. There's nothing too special there. Now, what if I change it to that notation that we had previously? If I do 10 with an angle of -150 instead? Well, my calculator just spits out 0 once again. Okay? Because like I said, they're pretty much the exact same thing. Okay, so this tells us that we solved this circuit pretty well. For fun, we can go ahead and just calculate the power factor here. So what's the power factor? Well, the power factor is just cosine of that angle. So that's going to be cosine of 30, which I'm pretty sure was 0.866. Well, maybe 886. No, 866. Okay. So that is going to be the power factor for this case. So that means for every 1 VA we send out, 0.866 of that is going to be watts, and then the rest of that is going to be VAR, or reactive power. Okay, so we're done with this circuit. We've made sure that all of our checks have checked out. Everything is making sense to us, so we're done with this circuit, and we know the power at each of these components. Let's move on to this next one. So number 5, this one's going to be a little bit different, kind of similar. We're going to have a 10 angle of 0 source again. This time we have a capacitor. So this is minus J 4 ohms. I gave this to you in impedance again, not capacitance. Okay, and then we're going to have a resistance. And this resistance is 12 ohms. Right, so now this capacitor, I'm just going to give you some more information, has a current of 2.5 with an angle of 90 degrees. Okay, so the current leads the voltage, or the voltage lags the current, which is what we expect. And this resistor has a current of 0.833 with an angle of 0 degrees. Okay. So now let's calculate the power in each of these components. And I'm going to do it in a little bit less detail, and this time now that we sort of know the formulas. Let's calculate the apparent power in this resistor. So this resistor has a voltage of 10 with an angle of 0. Remember, apparent power is 1/2 VI conjugate. So if I do 1/2 times V, which is 10 angle 0, times I conjugate, well, I conjugate is still the same thing as I because we have an angle of 0 degrees, so times 0.833 angle. You can put -0 if you want to. It doesn't really change anything. So that's going to give us 4.165 here. Okay, and we're talking about apparent power, so let's do VA. So you can see it's purely real. There's no angle involved, so purely real. That means it's all real power, which is what we expect in a resistor, so we're doing good. Now, for this capacitor, same formula, 1/2 VI. So the 1/2 and the V are all the same because they're connected in parallel, so it'll be 1/2 times 10 angle 0 times I conjugate. Sorry, I need to make sure you have that conjugate. So I is 2.5 with an angle of 90. The conjugate is going to be 2.5 angle -90. Okay, so this is going to be 12.5 with an angle of minus 90 degrees. Okay, so 12.5 with an angle of minus 90 degrees. So this is the apparent power for the capacitor, apparent power for the resistor. Let's calculate the apparent power for the source now. Okay, so let's do, for the source, this is going to be 10 with an angle of, oh, sorry, getting ahead of myself. So this is 1/2 VI conjugate. We know V is 10 with an angle of 0. I, let me make it mark up here. Let's calculate I total. So IT. That's going to be 2.5 with an angle of 90 plus 0.833 with an angle of 0. Oh, yeah, make sure I put parentheses around them because the calculator doesn't work otherwise. So the total current being supplied is 2.64 with an angle of 71.6 degrees. Okay. So overall, the voltage is leading, or the voltage is lagging the current in this circuit, so that tells us that it's more capacitive. Okay. So the power that's being supplied by the source is going to be equal to 1/2, so 1/2, times V, which is 10 angle 0, times I conjugate. So I, in this case, is going to be 2.64 angle conjugate, so we're doing negative 71.6. Okay. Now, there's one thing we've forgotten so far, and hopefully you caught it, but since this is a source, remember, we're measuring the voltage across like that way. So the total current is flowing into the negative port, so we need to have a negative here. So this is going to give me, oh, I didn't include my negative, even after I told you to. This is going to give me 13, oh, switch pins. So this is going to give me 13.2 with an angle of, make sure I'm doing this correctly, or negative 71.6 degrees, and this is a negative 13.2 with an angle of negative 71.6. Okay, so in an ideal case, we're expecting the apparent power to be equal to the total power being consumed, or we're expecting the source to supply enough apparent power for everything else. So let's check out the total apparent power that's being consumed. So that's going to be 12.5 with an angle of minus 90 degrees plus 4.165 with an angle of 0 degrees. And if we plug that in, we'll get that we are consuming 13.2. So let me move it over here. S total. We are consuming 13.2 with an angle of negative 71.6 degrees. Okay. And we're supplying negative 13.2. So we're supplying as much as we're dissipating. That means we did a good job on this one. Everything is making sense. So one thing that you can notice is that here we have this negative phase, right? We have this negative phase. Now up here, whenever we were dealing with an inductor, right, we had an inductor in this circuit, and we had this positive phase here. So the phase can actually tell us quite a bit about the circuit, right? So that can tell us, if we have this positive phase, that means we're consuming positive reactive power. And if we're consuming that positive reactive power, the only thing that consumes positive reactive power is, look here, this is consuming a positive reactive power. It's an inductor. So if we have a positive apparent, or an apparent power with a positive phase, that tells us that this circuit is more inductive, right? And that makes sense here. This doesn't have any capacitors in it at all. So of course it's inductive. For this one here, it's all capacitors and resistors. Okay, so this one is more capacitive because it has this negative here. So having that negative phase means it's going to be more capacitive, because a capacitor consumes negative reactive power, okay? Because this is the same thing as negative J 12.5 degrees. So capacitors consume negative reactive power, inductors consume positive reactive power. So looking at the total apparent power, we can tell if a circuit is more inductive or more capacitive. Okay. That was a little bit of a tangent, but that's something that's good to know here. So now let's move on to our last one. So our last one is number 6. Let me scroll down on my notes so I can get the circuit diagram. Okay, so for this one, this is a little bit of an interesting case, and this is going to lead into something that we're going to talk about even later. Okay? So what we have is we have a source, we have an inductor, a capacitor, and a resistor. Okay. Now this inductor is going to have an impedance of J 4 ohms. This capacitor has an impedance of negative J 4 ohms. And this resistor has an impedance of 8 ohms. Alrighty. So what we can see is that this capacitor is consuming 2 with an angle of minus 90 degrees current. The inductor is getting that 2 angle minus 90 degree. The capacitor is getting 2 angle 90 degrees. And this resistor is just getting 1 angle 0 degrees. So we have a little bit more stuff to calculate here because our circuit's a little bit bigger, has more components, but we know how to do all this stuff. So let's start off with the resistor. Apparent power for the resistor, 1/2 VI conjugate. So if we plug that in, that's going to be 0.5 times V, which is 8 angle 0, times I conjugate, which is going to be 1 angle negative 0. And that's going to give us 4 VA. Now let's look at that capacitor. So again, it's 1/2 VI conjugate. Now, in this case, our V is going to be the same. So 1/2 times 8 angle 0 times I conjugate. So that's going to be 2 angle minus 90 degrees because we're worried about the conjugate. Okay, so minus 90 degrees. If we multiply that together, we'll find that we are consuming, make sure I plugged everything in correctly, that we are consuming 8 with an angle of minus 90 degrees VA, or this is the same thing as minus J8 VA. Now let's do the inductor. The inductor, again, 1/2 VI conjugate. This is going to be 1/2 times 8 angle 0 times 2 angle. The current is minus 90, so we want the conjugate, so we're going to do plus 90. And that is going to give us 8 angle 90 degrees VA, which is equal to J8 VA. Okay. So now, if we add all these together, we add all of these apparent powers together, what we're going to see is that these two sort of cancel out, right? So what we see is that the capacitor is consuming a negative reactive power. The inductor is consuming a positive reactive power. So overall, they just cancel each other out. Okay, because if we have a J8 plus minus J8, those two just cancel each other out, get rid of each other. So the only thing we're left with is 4 VA from that resistor. So I'm just going to make a note here. That's SL plus SC plus SR. Okay, and that's what's equal to 4 VA. Okay, so now let's look at the source. So for the source, we're going to need to know this total current. So this total current is going to be just the sum of all those currents shown in red. So it'll be 2 angle minus 90 plus 2 angle 90 plus 1 angle 0. Oh, didn't get my parentheses on that one. And what we'll see is that this is just 1 angle 0. So again, the capacitor current and the inductor current cancel each other out. So if we calculate the power for the source, or the apparent power for the source, that's going to be negative 1/2 because we're going into this negative terminal here. So negative 1/2 VI conjugate. And what you can see is that that is going to give you 4 VA. Okay? This is something that we did, this is a calculation we've done before, so I didn't repeat it here, but we're going to get 4 VA. So what you can see is that the apparent power that we see is purely real. We don't have any sort of reactive power at all. So we have a power factor of 1, which is good. That's what we want. We want a power factor of 1 because we're not wasting anything on reactive power. And the reason this happens is because the inductor and capacitor sort of complement each other, right? Because we said that an inductor and capacitor, they're going to store a little bit of power and then release a little bit of power. Store a little bit and then release a little bit. And what actually happens is that whenever you have a setup like this, which, like I said, we're going to talk about this in more detail later on. I'm just covering this very, very briefly. But whenever we have a setup like this, you can actually make the inductor and capacitor sort of feed into each other. Okay, so the voltage source, that 8 with an angle of 0 degrees source, isn't having to supply anything to that capacitor and inductor because they're working against each other pretty much. So whenever the capacitor is releasing that power, the inductor is just consuming that same amount of power. And then whenever the inductor is ready to release it, the capacitor is ready to consume it. So they sort of just feed it back into each other. So if you look at this circuit here, there's power going here, and then after a little bit, it's going to flip backwards. Okay, so that power is just going back and forth. It's like that capacitor and inductor isn't even there. Okay, so like I said, we're going to talk about this setup later on. This is called a resonant circuit. Okay, but like I said, we're going to talk about this in more detail later on, so don't get too confused with this. Okay, the main thing to know is that we are supplying 4 VA, we are consuming a total of 4 VA, so that circuit makes sense, and we've pretty much solved all the powers in this circuit. So guys, I hope you enjoyed this video. I hope you found it informative and that it maybe cleared up some of these formulas that we talked about in the previous video. If you have any questions, please feel free to leave them in the comment section below. I'm happy to read through any questions and answer them to the best of my ability. Otherwise, if you like this content, please give me a thumbs up and subscribe. And I'm Aaron Carmen. Thank you for watching.